In 10.7, we talk again about valence bond theory, and we expand on the unhybridized orbital aspects of it that we saw in section 10.6 to start talking about the hybridization version of valence bond theory that we're now going to see in this section of the chapter. So if we look at carbon and hydrogen and how carbon and hydrogen might bond, we could look at this and say, all right, we have two orbitals that don't have paired up electrons in carbon's 2p level. So perhaps we have two hydrogens that could come in and take up a space and share their 1s orbitals with carbon's 2p orbitals and get a very similar structure for something like CH2 compared to what we saw with SH2 previously. Now, that would be a theoretical prediction with unhybridized orbitals. What we really see, though, is a tetrahedron formed, like we have been talking about when we have talked about shapes, and that leads to angles of about 109.5, which is a nice symmetric tetrahedral arrangement of atoms. So what's the difference here? What's going on differently? Well, what's going on differently here is we are actually getting a hybrid set of orbitals where we've combined the s and the p orbital in their wave equations from chapter 7, and those are combined to form new solutions and thus new shapes at a new energy level. And the energy level is between the 2s and the 2p for carbon, and we have four, instead of these four orbitals with 1s and 3p, now we have four different sp3 hybrid orbitals that the electrons can be in and bond with hydrogens in. So how do these combinations work? Well, if we have an s and a p orbital, this has a much better set of diagrams than I could draw by myself. We get one orbital where the positive nature on the right side is amplified, and in the same p orbital, shifted around a little bit and mixed with an s, we get a large positive lobe and a small negative lobe on the other side. So overall, with the two orbitals, we get two large positive and two little tiny negative lobes that we can use to stick in different directions. And that's just with an sp hybrid, where we're just combining two different orbitals like we would with a linear molecule. When we combine 1s and three different p orbitals, then we get sp3 hybrids like we do in methane, like we were just talking about, see carbon and hydrogen together, and these point towards the four corners of a tetrahedron when they're combined in this way. And that's where we get this 109.5 degree angles between these sp3 hybrid orbitals. So here's our overlap. We have we have carbon, which has four sp3 hybrid orbitals. So we can say 1, 2, 3, 4. In terms of these are two sp3 hybrid orbitals. Okay. So these, since carbon has four valence electrons, are all singly filled. Okay? We used to have 1s, or 2s, and 2p for the valence electrons in this arrangement, but now we have this sp3 hybrid arrangement, all at the same energy level. Well, each of these is going to bond with or overlap with a 1s unhybridized hydrogen electron, and there will be four possible hydrogen electron bonding positions here because there's four open slots basically, leading to overlap between hydrogen's 1s and carbon's 2 sp3 hybrid orbital. Okay? So this model, this valence bond model, where we're looking at overlap of hybrid orbitals with unhybridized orbitals, shows us a different model for C carbon and hydrogen bonding, specifically one that will lead to 4 hydrogens bonding to the carbon at equal distances apart from each other, which in reality, when we measure these distances of the molecule bonds, is more in line with what we actually see. Now, ammonia, NH3, if we look at the Lewis dot structure for this, we end up seeing 3 bonds to hydrogen and 1 lone pair of electrons. So we have 4 groups which are trying to get as far away from each other as possible. So we again cache in our 4 orbitals, 1s and 3 p's, for 4 equal sp3 hybrid orbitals. And in those, we put nitrogen's electrons in that section, and its lone pair of electrons in one spot. So here we have the lone pair. And then hydrogen again can come in and bond with, by overlap, 3 different positions, here, here, and here, where a 3p orbital and a 1s orbital form a covalent overlapping bond. And so this works pretty well not only for a direct overlap, like we just saw, but we can look at also the difference between a direct and an indirect overlap, or a sigma versus a pi overlap. Well, we've seen the first double bonded structure that we looked at in our Lewis structures was CH2O, which has the following Lewis dot structure. So we can see there's 2 bonds to the oxygen, and when we arrange hybridization, we only have 3 directions that the carbon has electron density. So that means we take our s and p orbitals and we trade in a couple of them, just the 3 for the 3 different directions, to get sp2 hybrid orbitals and a remaining 2p orbital on the oxygen, or the 2p orbital that is not hybridized. So that not hybridized 2p orbital is still going to be in the carbon. So the sp2 hybrid orbitals are having a direct overlap with the 1s orbitals of hydrogen. So we refer to these as sigma bonds. It's a Greek symbol, lowercase sigma. So all 3 of these sigma overlapping bonds. Okay. Now the p orbitals, which stick up from the carbon, up and down, so this is the positive and negative aspect of it, can interact with the p orbitals on the oxygen. So this overlap then stretches across above and below the plane of the trigonal planar arrangement of sp2 orbitals and gives us a second bond. So the top and bottom together is one secondary or pi bond, and that's between the unhybridized p orbital on carbon and the unhybridized p orbital on oxygen. So how can we describe this? Well, we can describe this as carbon's bonds. We can say carbon has 3 sigma bonds, and those 3 sigma bonds are situated between carbon's sp2 and hydrogen's 1s, and we have 2 of those. And we have a carbon sp2, that's this purple one right here, and an oxygen unhybridized 2p orbital, that's here and here. That's our sigma bonds. And then carbon also has an interaction with oxygen where it has one secondary or pi bond for the multiple bond between carbon and oxygen. And that happens between a carbon 2p orbital and an oxygen 2p orbital. Excellent. So what are the differences between the single and the double bonds when we look at it through this theory? Well, if we look at dichloromethane, this C2H4 Cl2 molecule, which is arranged with a Lewis dot structure, something like this. There's some extra electrons around here, but those won't matter at the moment. We can see the sp3 hybridization, so we have a tetrahedron here. And a tetrahedron on the other side as well, but the carbons are overlapping with sp3 orbitals. And this says hydrogen, but I think their diagram is confused, because this is an sp3 to a carbon sp3 orbital. Okay. And the other two spots on that carbon are sigma carbon sp3 to hydrogen s orbitals. And we even have, wow, I got this straight from the book too, goofiness. Right here we have carbon's sp3 orbital interacting with a chlorine 2p orbital. And we have this on both sides effectively. There's no double bonding here. And because there's no double bonding here, we can actually get free rotation about that single bond. When we just have a single bond, this can actually twist around. So this chlorine can go all the way around and point in all sorts of different directions on both sides. Now with a double bond though, this double bond actually creates a second center of attachment. And being a double bond like that, with the second attachment, prevents rotation from occurring. So in reality, not only do we see this molecule, but we also see this version, which is actually different. These are two different molecules with slightly different chemistries and slightly different physical properties, just because that free rotation is not there around the bond, so I can have the chlorines both on the same side, which naming wise, which you don't need to remember, is referred to as a cis arrangement, or chlorines on opposite sides, which is actually a trans arrangement in terms of naming. Now with a triple bond, we have even more excitement here. We're looking at ethylene, which has a Lewis dot structure, ethine, of C triple bonded to C with a hydrogen on either end. Here we're seeing a carbon sp hybrid with a hydrogen 1s, and that's because since we only have two directions, 1, 2 for each carbon center, we only need to hybridize two atomic orbitals into two sp hybrid orbitals. The remaining p orbitals stay unhybridized, which is good because on both carbons they overlap. So we have one p secondary overlap pi bond, and we actually have then a second p, that's kind of in the back here, it's hard to tell, overlap with the carbons as well. So top and bottom is one additional bond, front and back is a second bond, giving us a 3 altogether when we also include the sp3 hybrid to sp3, or I'm sorry, sp hybrid to sp hybrid carbon direct sigma overlap in the center. So if we're going to describe the bonding here, we'll call this carbon 1 and this carbon 2. On carbon 1, we have two C sp dihydrogen s sigma overlaps. Right? Take that back. We only have one. We have this one right here. The other one's on the other carbon. We have one carbon sp to the other carbon sp sigma overlap. It's right here. And then we have two carbon unhybridized p to other carbon unhybridized p pi attachments. And that's on each carbon. Carbon 1, carbon 2, same thing. Now when we get to higher order hybridization, it gets pretty ugly when we try and figure out where the pi attachments are. So for this particular theory, we're not going to get into that. We're just going to look at sigma overlaps. But if we look at, say, arsenic attaching itself to 5 fluorines, here's our Lewis structure. Arsenic, if it has 5, we have d orbitals, p orbitals, and s orbitals that will need to hybridize. With 5 attachments, I will need 1, 2, 3, 4, 5 orbitals. So with 5 orbitals, that means I have an s3p. That's what the little superscript over the p means. It means 3 of those orbitals involved, and d hybrid orbitals. And since I've used 5, 1, 2, 3, 4, 5 orbitals, I get 5 of these hybrid orbitals. So when I get these 5 hybrid orbitals, I'm going to overlap those with p orbitals on the fluorine. It's not attached to any other atoms, so it does not need to hybridize. So here it is with 5 sigma, that's direct, overlaps between an arsenic sp3d orbital and a fluorine unhybridized p orbital. Now with sulfur hexafluoride, we can see exactly the same sort of thing. The only difference is we need a second d orbital to contribute to the hybridization process so that we can have 1, 2, 3, 4, 5, 6 orbitals altogether for hybrid orbitals.